the camera cut off just as I was explaining that this vector representing the position r of t sub I star could be a random, that t sub I star could be a random selection. This could be any vector between here and here. If this is a very small interval, there's not going to be much difference between one selection of the t sub I star and another. The r of t sub I star will lie within a small interval. Now we're going to take the derivative of our r of t sub I, and I'd already written that down when I thought the camera was still on, but we're going to get r prime of t sub I star, and that's going to indicate the rate of change of the r vector with respect to t at this point. If t is interpreted as time, so that this is an object moving along the curve in time, then this is just going to be the velocity, the derivative of the position function, and we're quite familiar with that by now. In any case, this is the rate of change of the r vector with respect to t at this particular point, and we expect that rate of change to be the same for all points, to be very nearly the same for all points within a small t interval, from t sub I to t sub I plus 1. In this case, the distance moved along this arc is just going to be what? Well, it's going to be, first we'll denote it delta s sub I, and that's approximately equal to the product of the r prime vector and the delta t sub I, the magnitude of that vector. Now the r prime of t sub I, delta t sub I, is a vector that's very close to the vector delta r from this point to this point. We've depicted that vector before, about this big. Since we're choosing an arbitrary sample point, the r prime might be a little bit different than it would be if we took an average of the r primes. Therefore, we call this an approximate equality. As delta t sub I approaches 0, this r prime vector is not going to have much room to vary. It's not going to be able to vary by a whole lot, so that this approximate equality becomes an equality. Now, what do we mean by delta t sub I here? That's the time interval corresponding to this change in position here, to this segment of the curve, and delta t sub I is just t sub I plus 1 minus t sub I. We go back to our partition. We're partitioning into typical intervals, and the delta t on any interval will be the change in the t from the beginning to the end of that interval. Now, looking back at what we have here, our positions correspond to the points r of t sub I and r of t sub I plus 1. We now have an expression for the approximate distance traveled on this interval. This interval is arbitrary. We don't know what I is. It could be 1, 2, 10 million. It could be anything, any time interval in this partition. For any time interval within this partition, this is the approximate distance. So that the total arc distance from the point given by r of A to the point given by r of B, if we move along the curve, is approximately what we get when we add up all the delta s sub i's. And we're adding these delta s sub i's over all the intervals. I'm not going to throw in the subscripts here. If we want to get rigorous, we're going to have to be just a little more careful. But this is the structure of the argument we would use. So we add up all the delta s sub i's, and as our delta t sub i's approach 0, now just exactly what that means, Again, there's a technicality involved with what we mean by this, but intuitively, if all these intervals uniformly get small in some way, the sum of delta S sub I approaches the actual arc distance, because we're simply adding up approximations to the arc distance over the entire path, and these approximations get better and better as our delta T sub i's get smaller and smaller, leaving our R prime of T sub I star less room to wiggle around and cause discrepancies. Now the limit, and again I'm not being real rigorous here, I'm going to say with delta T's going to 0, probably have to say delta T sub I is going to 0 of the sum of delta S sub I is the limit as our delta T sub i's approach 0 of this expression. Okay, this is the absolute value of R prime of T sub I delta T sub I. I'm going to put my absolute value signs here, and probably should have earlier. Delta T sub I is assumed to be positive, so it doesn't really make any difference. But if I write it this way, what is that limit? Well, if you go back to the definition of an integral, that is just the integral from a to b of the magnitude of R prime of t dt. So our arc distance between the points is just this integral, and we'll see how that works out for a couple of specific examples.